That is correct. Yes, I'm going to talk about wave equations. I'm told that everything should be visible on the recording now, so I wear a microphone because of that. So wave equations in subextremal Kerr-de Sitter spacetimes. This is a topic that really Andras was starting to study, and we've done some results in this together now. So this is joint work with Andras Vasy. So I will introduce Kerr-de Sitter spacetime slightly differently. So Alan introduced them yesterday in sort of a different way. So just to complement that, I will sort of talk about it from a slightly different perspective, just like maybe introduce more sort of a physical physics or physical space first, and then go to the Penrose diagrams and so on. Okay, so as we all know, what what we want to study is some very large mass centered at the point or as close as possible. This is a positive mass. This causes this region around where nothing can escape because of gravitational field, and this is the black hole. So this is the event horizon. And of course, if something falls into the black hole, you might imagine that this massive object picks up some angular momentum, so it's natural that like typically will rotate with the angular momentum A. Okay, so this would be the object that is described by the Kerr spacetime, right? But of course, we're in an expanding universe here, so the Sitter part. And the expansion causes this second cosmological horizon. So it's like another horizon which is far away, very, very far away from, like, the radius through the cosmological horizon is much, much, much bigger than the radius of the event horizon, like extremely much bigger. So what is that? What is sort of one way of imagining this cosmological horizon could be that, well, imagine that you're in an expanding universe and you have some observer who's very, very, very far away, and he or she tries to send you a signal, you know, as fast as possible, so it's a light signal. And just due to the expansion of the universe, that light signal will never reach us. It's like, you know, that person is just sending us light, and it's just like the universe is expanding so much that the light will never reach us. So this causes this extra cosmological horizon around, at least from the point of view of black holes, from like point of view of the black hole. Well, we're maybe sitting here. This could be, in this model of the universe, this would be here, but this distance is thought of as extremely much smaller than this distance. So we're like approximately at the black hole from the perspective of the cosmological horizon. But of course, this radius to the middle of the black hole is also extremely much bigger than the radius of the actual black hole. Okay, so what I'm interested in today is sort of the thought experiment. So I should say that, I guess I said it, but let me just write down cosmological horizon as well. So what if we had some perturbation, let's say the gravitational field or just some other field? You might want to perturb, I mean, most complicated would be a perturbation sort of the pure gravitational field, but you can also imagine it being initialated to any sort of linear wave equation, if you like. You would imagine somehow that the energy disperses, and eventually some energy is going to fall into the event horizon, and some energy is going to fall past the cosmological horizon and just sort of disappear. Well, no energy disappears, right? But it gets hidden behind the horizons. So from our perspective, that would mean that we have some decay. So of course, nothing disappears, but you just like, from the perspective of this analyst where we live, it's not there anymore. It's never going to be visible anymore. Okay, so this is the question. But of course, you get to the first sort of, I mean, this looks reasonable, that the energy will just sort of disappear. But of course, you get to the first, where should I draw this? The first sort of obstacle, namely the trapped geodesics, so the trapped light. So as we all know, around the black hole, in principle, there could be light that is trapped for an infinite amount of time, just like, you know, some massive object just orbiting the black hole. Just like that, light could also be trapped around the black hole. And you could then imagine by some geometric approximation or whatever you want to prefer to think about it, that some energy is staying along those light rays for a very, very long time, sort of contradicting or counteracting this picture that we have in mind that the energy should disperse and fall into the black hole. The energy could for a very long time stay near this trapped light. Okay, so trapping is going to be one of the issues here. So in this talk, I will describe sort of a new result in this setting where we don't have any restriction on the angular momentum other than this being sort of well-defined. This is what this subextremal means. I will describe by this in a minute. And sort of the key point is that, well, it was known I mean, the theory that Andras developed in 2013 was a it's an asymptotic expansion of waves in general, but it only worked, at least in the way it was written, for a not very small, but satisfying. So it's like a large range of A, but satisfying some certain bounds in terms of M. So, but the framework was very robust. So the only thing that we had to do to generalize this to an arbitrary angular momentum was to check sort of or show some geometric stuff about Kerr-de Sitter. So in our paper, there's my talk today will mostly be actually about sort of the geometry of Kerr-de Sitter. So some novelties there. So the microlocal framework just worked after checking those features. So let me go back to what I'm looking at here more formally. Well, this is going to be a solution to the following equation. So reach of G equal to lambda G, where lambda is the positive cosmological constant. That's the third parameter in this picture. So causing, if you will, this cosmological horizon. So then we have the result by Hintz and Vasy that I'm sure you all have heard of from 2018, which says that the spacetime is non-linearly stable, so non-linear stability. If A is much smaller than M. Okay, so you have some slowly rotating black hole, then it's actually proven to be nonlinear stable, and this is also what Alan talked about yesterday. Okay, but so the natural next question is, how about or how to drop the assumption on A? Well, you got to have some assumption, right? You want to be in the subextremal range, but you know, how to drop the assumption on A that it should be very small. So the first step towards that would be to show decay for linear wave equation. Or a natural first step. And that could be written sort of in terms of and I guess the microlocal analysis world or the scattering theory world, you would think about this as an asymptotic expansion, like proving this in two steps. You have an asymptotic expansion plus mode stability. That's sort of the approach. So I will tell you exactly what those two are just as we go along the talk today. But I just wanted to mention at this stage that this is now the part that we have done in complete sort of generality. Actually, there's some very recent result, which is sort of giving a new perspective also on this, based on, of course, Vasy's analysis that did this for a large range of A already in 2013, and also other authors before. And this mode stability is known if A over M is very small, or if, so roughly speaking, or if lambda M squared is very small. So these are like the scale invariant quantities. So there are, I mean, Kerr-de Sitter has 3 parameters, but you know, modulo scaling there are only 2 parameters, and this is one of them. This is the other. So the other one, sorry, Peter, I'm losing space here for your name, but this is due, the second one is due to Peter Hintz in 2021. I think I got it there. So this is sort of when this parameter, you think of it, it's like, you think of it as lambda being very small, and then Peter was able to show mode stability using the result which is known for lambda equal to 0, namely by the Whiting transform. In Kerr, it's known mode stability, so he was able to use this. This is another limit, which is sort of the Schwarzschild-de Sitter limit. When you let this be equal to 0, it's the Schwarzschild-de Sitter metric, and then you can use perturbative arguments to get there. So Hintz proved this result very recently. Okay, so mode stability is known in some cases, but open in general. So what is the asymptotic expansion? That's what I want to describe now. But before that, let me recall what the Kerr-de Sitter spacetime is. So of course, please interrupt me with any questions at any time. So the definition is as follows. So it's subextremal Kerr-de Sitter spacetime is the following. So the manifold is given by RT, so this is like the time, and then we want to cross it with exactly this picture. Because the only thing that I didn't draw here was time, right? So there is like, if you think of this as sort of being rotationally symmetric, it's not really, because you have some preferred rotation direction. But apart from that, this annulus cross time is what we're looking at. This is RE, RC, with the parameter R, and then you have S2 at each point. With the metric, so phi and theta, the other phi and theta, with the metric given by the following. So this function, I will not introduce precisely what it is. It's just some positive function that we don't need to care about. This mu of r is a polynomial that is actually very important, so I will write out what that is. C of theta is just some function which is positive we don't care about. I mean, for algebraic computations you would care, but for the purposes today, it's not important what the C of theta and the rho of r and theta is. And the b squared is just some constant, which is also positive. A dt minus r squared plus a squared d phi. Actually, I'm just writing down the explicit form of the metric because I will need it one step in the proof just for some simple check. You can see sort of one of the main points, you can actually see it very easily from this formula. So if anything looks strange, it's probably because I've done a typo, but I hope this is more or less correct. So we have like one sort of time direction. This is this minus sign, and then you have pluses. Okay, where now? Let me write it over here. Where the mu of r, that's this polynomial that I was talking about, so if lambda was 0, you can maybe recognize this sort of, if you're used to the Kerr metric, and this one disappears, and you only have r squared minus 2mr plus a squared. So this is the polynomial whose roots are going to define the position of the horizons. So we want this to have, so we're still talking about what subextremality means in this case. So this is supposed to have 4 real distinct roots. And the roots are called, in our setup, it's called R minus, as a negative root, which has no sort of physical meaning. It's just there in the equations. Then you have the place, the radius for the cosmological, for the Cauchy horizon, or the inner event horizon. Then you have the outer event horizon, or simply the event horizon, RE. So this is a capital C for Cauchy. This is a small c for cosmological, okay? So this is event horizon. So this is the place that we're interested in. So this is of interest here. So this was exactly like in Alan's talk yesterday, that we only cared about the two largest roots. Those are the ones that are defining this region where we live. It's going to be a huge region typically in the physical world, but for us, this is just all we require. Okay. Then you can immediately start with a remark. And that is to say that if I look at now, so this was a claim that I think that Alan said this yesterday, that if you either look at the event horizon or the cosmological horizon in the metric and you compute what g of dt is, well, this part of the metric will not contribute, right? There's no dt or something in here, right? There's no one form dt here. This one will also not contribute because the mu is equal to 0 at its roots. This is gone, this is gone. So, and this is of course also gone. So it's just this funny positive number times a squared. So in any case, this is positive. So this is the claim that Alan said, that, well, if you look at this dt vector field, it's actually going to be space-like at both. So like if A is not 0, because if A is equal to 0, then it will be light-like. Then this vanishes. So, so we're going to have so the time direction is sort of space-like there and space-like here, which gives you two ergo regions, namely the regions where it's sort of space-like. Well, that's some region around here and some region around here. So you have two ergo regions. Okay, that's something to remember. And if so, Andras showed in his paper 2013 that if A is large enough, or I mean, this is not so clear exactly how to formulate this, but there is an A large enough such that the ergo regions intersect. And this is from a PD point of view, this is a disaster, because what if the bad regions, they suddenly start to intersect, like they're eating up everything, so we're not even time-like anywhere, right? And preferably you want a time-like Hilbert vector field everywhere. And you're not you're not going to be, if you take the formulas, there's always going to be some region where it's time-like, but like the ergo regions intersecting is a bad thing. Okay, but this can happen. Okay, any questions so far? So in Kerr, this is not going to happen because this is chosen in a way. So maybe one can, I shouldn't compute at the blackboard, but formally it's the same formula for Kerr, right? So, and if you go off to infinity here, like spatial infinity, this is always going to be time-like. That's the unique Hilbert vector field that we feel is time-like, because we're far away from the black hole. We're outside this isolated system that you're looking at. So this is not going to happen. Well, first of all, you don't have something. Well, you could have something reminiscent of a second ergo region, but for this choice of stationary Hilbert vector field, you don't in Kerr, because this is the unique one which is time-like. Hope I answered your question now. So very far away, sorry? Yeah, so then this is time-like, yeah. And it's going to be like very far away, and it keeps on being that the further you go. Okay. So usually when I give this talk, I'm talking a lot about the Penrose diagram, but I'm just assuming that you know what those are. So let's draw the picture. So this is unfortunately as non-square as it usually is. So this is the region in between the horizons. So this is the future event horizon. R equal to RE, and here you have the future cosmological horizon. So what will be in a Kerr, typically the plus null, so future null infinity is now the future cosmological horizon. And it is located at the bigger radius R equal to RC. So what I've done now is that, well, this coordinate system that I wrote the metric in is the Boyer-Lindquist coordinate system. And as you can see, as we approach R going to RE and R going to RC, we're approaching roots of the mu, so all of this expression is just blowing up. So for each horizon, you have to do this standard coordinate change to extend the coordinates over the future horizons. Just like you usually do for Kerr or Schwarzschild, over one horizon, you need to do that for both here, and preferably simultaneously if you want to have sort of one expression for the entire metric. But this is not going to be the exact expression for the metric if exactly you are at the horizon, only beyond or in between. Okay, but so after doing that, you get a new time coordinate where such a line is t star equal to constant. So I've now changed to t star and phi star. I can actually keep r and theta, it turns out, but t star and phi star have to be the new ones. And I'm interested in sort of, I think of it as being some foliation like this. And one of these guys, I'm going to call that T0. Because I will use this to formulate the initial vary problem I'm interested in. But what we want to do is we want to solve the following. So box plus some first order part, zeroth order part, u equal to f, where I want u to vanish past of some hypersurface where t star is equal to t0. I want it to vanish here. So u should be identically equal to 0 here, and I have some f, which has some support. I mean, if you want to be very precise, it has some decay. We think of the support of being here, for example. And then you're starting with 0 data, and you're solving to the future. So this is in the domain of dependence. This part is in the domain of dependence, like the future of this is in the domain of dependence, not the past, so you better solve it only to the future. It's not a kosher hypersurface for the entire thing. It's a kosher hypersurface for a little bit smaller. But this future part is in the domain of dependence, so you can solve it to the future, and then simply check what kind of bounds do you get on your solution. That's a decay. So, unfortunately, we're not able to prove that because we don't know that mode stability holds, but we can do everything else. Everything is done but the mode stability, that's the statement. So this is the result from 2021. Where is it? Analytic framework is Vasy's, and then other authors contributed on the way. So this extended space-time is now going to be called M star and G star because everything with a star in my notation means extending it over the horizons. I have an M star and a G star, and I'm thinking about that as the extended space-time. So like extended over the horizon so that I can even talk about this initial vary problem. Kerr-de Sitter space-time. So then, apart from a finite dimensional space of very annoying solutions, the function decays. So then there exists a c greater than 0 such that the following holds. U t star x. So x is going to denote all the other coordinates, all the coordinates in that picture. So like I want t is a time coordinate, and x is just a point in this picture, right? So it's just like r, theta, phi, and so on. So this is cheating a little bit because I should really write sort of, there could be multiplicities. So that will give me an extra factor of t here, which I don't care about in writing this. So this is now exponentially bounded. That's the statement. Where sigma 1, sigma n, capital N, they're complex numbers. This is also a statement that we saw in Alan's talk yesterday. Or I think not the statement maybe like in this, written in this form, but very similar. So what does it say? Well, sorry, this is just an exponentially decaying function in t here for those who can't see that because of this thing here. If I ignored this term for a moment, like let's just say that this finite sum is not there, well, then it would be exponential decay, and it's very desirable to do exactly that. But we can't, right? I mean, in general, you have this extra sum here of solutions of a very particular form, namely this product form. Okay? So you have a finite sum, which we cannot exclude. And that is the mode stability part. The mode stability says that this sum is not there. Yes, please. Sorry, say again? Right, so you can have multiplicities here. So you would have a polynomial in t, which I just ignore. And also there are corresponding estimates also for the derivatives and so on, and you have sharp assumptions on f and blah, blah, blah. But this is the essential feature of the statement. So just to draw that picture that Alan had yesterday, so these are called quasinormal modes or resonance states. And in another paper, we show that actually these functions are real analytic. So they are very nice, very special functions, very special solutions, but we still can't exclude them. So what is the problem of having those? Well, this is the complex plane, and you have a lot of these numbers here. This is the sigma 1, maybe sigma 2, sigma 3, and so on. So the first one is maybe equal to I. Let's say it's equal to I. You want to check what happens to this term. Well, x are sort of the spatial directions, nobody cares. Nothing is going to change in t here. But if I plug in sigma 1 being I, we can compute it's e to the minus I squared. Well, that's e to the 1 times t. That's exponentially growing. This guy is really bad. We don't want this guy, right? Because it would mean, the result would then say that the function is only decaying up to subtracting an exponentially growing thing. So the function is not decaying. We want to exclude, we want to get rid of this guy, preferably. In fact, everything which is above, I should include the real line, so above and including the real line, those should preferably be gone except for this one. Sigma equal to 0 corresponds to the constant solution. That will always be there. But except from this one, we should get rid of all those in the upper half plane, and that's the mode stability. And one might formulate this as a conjecture or not. I mean, I wouldn't dare to formulate it as a conjecture, but it would be desirable to prove the mode stability, namely that the imaginary part of all these sigma j's is negative, apart from sigma j equal to 0. At least, maybe it's too much to hope for in general, but maybe we can prove it when a is equal to 0. Maybe it's not even true in other cases. We had a discussion at lunch today in Kerr. It's actually not true if for the Klein-Gordon equation. So you have to be careful also with the 0th order term. Okay, so that would be good, because that would mean decay, because that sum would then only contain sigma j's, which have a negative imaginary part. So they would be exponentially decaying, just like the I was exponentially growing. The minus I solution that is exponentially decaying, it could be thrown over to this side, like modifying C potentially. That would be a very good thing. So mode stability is desirable, but open. And it is known, as I said, in certain special cases where lambda m squared is very small, or if A over m is very small. And it is known, and one can actually use this then to get a case. So A over m being small, that was already covered in Vasy's 2013 paper. So this is the full subextremal range. There's nothing more to be done there. So, any questions? I think I have all the formulas on the board still, and I wanted to talk to you about, a little bit about what the proof is. So, what was it that Andras required in 2013? Well, again, it was not smallness of A, but it was some other sort of algebraic bounds which come up for different reasons. So he required this. This is what I'm going to call 1. And he required this, which is what I'm going to call 2. And these bounds had nothing to do with the analysis in principle. You know, the analysis, it's the analysis. Everything was done. There is nothing to be done. But as so the analysis as it's written in this paper was not applicable. I mean, unless you had made some changes in the cases that you violate either one of these inequalities. So that's what I want to describe, what the ideas were to remove those, get rid of those. Well, so the first one is, so I'm going to write a 1 for this inequality, how we get rid of this, and a 2 for this inequality, how to get rid of this. So the first one, I remember us verifying this once we got the idea. It was very quick. It was very easy. So getting rid of the first one is actually very simple once you get the idea. So you want to use P being, so the question is what you want to use. What kind of vector field are you going to use to model the time invariance? Well, there was an issue, here it's written. So there was an issue about these ergo regions being too large. They might intersect. So there's something funny about this choice, at least if you're interested in large A, so fast rotations. This feature is undesirable, especially the second one here. We don't want that, right? We don't want the ergo regions to intersect. So it's a very simple idea. So redo the entire analysis with another vector field as your time invariance vector field. When we wrote this paper in 2021, we only had one particular choice of vector field, but in a recent preprint, we showed that we can actually choose a variety of vector fields that will work. So you can choose anything, you can choose this particular combination. So this is a Killing vector field. This is the classical time invariance, if you will. This is the rotational invariance. And you can combine any of the two with constants, and you have another Killing vector field, right? So we took this combination, and look what happens then. Well, then you could easily see that this vector field here, oh, this is heavy. So I hope you remember now the vector field by heart. So for those of you who haven't worked with Kerr or Kerr-de Sitter before, when you do this extension, the dt and the dt star, that's the same vector field. It's just that dt star extends over the horizon. So it's the same vector field if you restrict it down to the analysis in between. Okay, but so let's think about computing. So T was this dt. I'm going to write it without the stars now because that's what it is, where these coordinates are defined. But it's literally the same vector field, just extended. So if you have this, then you can compute what is g of t comma t at R0. So at R0, well, again, this is not going to contribute at all. This is not going to contribute at all when I evaluate this. Only these two terms will contribute. But if I want to evaluate it exactly at R0, I need to put R to R0 at that point. Sorry, yeah, so R0, sorry, R0, I should probably, no, I haven't really solved anything, right, but it's getting there. So, yeah, that's it. So R0 is any point in between, could be the boundaries. Okay, no, yeah, but we remember that now. So if I want to evaluate this, I need to evaluate this at R0, and if I did everything correctly, this guy is actually annihilating this vector field at R0. If I plug in here R0, I look at this one form, I evaluate this on this vector, well, it's gonna go away at R0. So I only get this function here. This mu is this polynomial, between the roots is positive, these guys are positive, this is gonna give something positive. Oh, with a minus sign, I get something negative. This is always gonna be negative. So I know that the ergo regions can never intersect anymore. So, you know, I have actually used that R0 is strictly in between the horizons now in this computation to really get negativity, because at the horizons this one disappears, and you have to look at derivatives to really figure out what's going on. Like you need to differentiate this expression and so on, blah, blah, blah. But let's just focus on this example for the moment. Well, then I have separated the ergo regions now completely, because I have at least one point in R in between the horizons where this is going to be time-like. So it's a super easy idea. But so the ergo regions are not intersecting, but you know, who cares about the ergo regions in the end? What we really care about is the following. How does Andras' argument for Kerr-de Sitter go? Well, you start out with saying, I have a time invariance. Like this is the picture that I like as a human and a spectral theorist and so on. This picture is nice, but the time is some time invariance that is another dimension that I neither can view, but on the other hand, it's a symmetry, right? So I should be able to get rid of it. So I start out with Fourier transforming in time, right? And then I look at the induced operator on this sort of space. So, but I did something there, right? I Fourier transformed in time. So if you think about it carefully, what you have done is actually your analysis relies heavily on a choice of time invariance, because you did the Fourier transform in time. So the choice that you do, the time invariance that you choose, is actually going to change the analysis. So you can do it with either of these choices, where R0 is this point that we discussed just before. Then the analysis will actually be quite good. So what is it that is actually relevant for the analysis? Well, it's all the light-like geodesics that are orthogonal to this vector field. Or in other words, the classical bicharacteristics for the new operator. But let's stay general relativistic here. You want to look at all the light-like geodesics that are orthogonal to this kilometric field. Okay, so the ergo region, they don't intersect. So the light-like geodesics that are orthogonal to this kilometric field, the first thing you can check is they can only live in the ergo regions. Why can they only live in the ergo regions? Because as soon as this is going to be time-like, and you're looking at a causal vector field which is orthogonal to it, well, that's not going to exist, right? There's a time-like vector field contracting with the causal one, well, that's not going to exist. So they cannot be orthogonal. So the ergo regions, that's where the light-like geodesics live, but we require not a condition on the ergo region, Andras requires something more. You require the non-trapping condition and the radial point structure, and so on and so forth. So let's look at what the light-like geodesics that are orthogonal to T, what they do. So what they do is the following. So you have some extra variables, but we'll throw them all out and just look at two variables, namely the R variable and the dual R variable. Okay, so the frequency in R. Here is maybe my RE, here is my RC, because in Riemannian geometry, the frequency doesn't change, right? Of a geodesic, it doesn't change. But the frequency changes a lot for light-like geodesics. So what happens for, I'm only looking at the light-like geodesics, so the T orthogonal light-like geodesics. I mean, since it's a T orthogonal, I really think of them as living here, and I only care about the radial coordinate, but I'm also checking their frequencies at all times. So what happens then is that they come out here, they typically go through here, and then I need to check this in which direction they go. This can be computed with the Hamiltonian. So now I have an arrow in both directions. I think this is the correct one. So something like this. This is typically how they go, the light-like geodesics. Yeah, so here is beyond. We don't care about that region. This is a little bit beyond. They always cut transversely there. But if you follow, for example, if you follow this one, it goes up to infinity. It goes radially out, right? It goes radially out in the fiber. That's why it's called a radial point estimate. So this is radially out. Radial. The key word is the radial point estimate. In fact, it's like a sink here that all the light-like geodesics go to, and in a similar way, there's a source here, like where all the other ones come from. So this is the source sink picture. And I guess, well, though I'm not an expert on that, well, this is also what people call the redshift, right? Because you have a frequency shift, like frequency going to infinity. So this is the analysis of these, and this is compatible with the picture that at and around this point R0, you cannot have any such light-like geodesics at all. There is at least a little region where you're safe. But what could happen if the ergo regions intersected was that, whatever could happen. I mean, many strange things will happen. But in this way, we're safe. Like, we have the structure, and you can check that they have the source sink structure, the radial point estimate supply, and this is the this is the key feature to start defining these quasi-normal modes. Okay? This is the step one. Okay, so the last 7 minutes I want to talk about step two. So this step actually alone produces, no, now the picture is gone. So the picture was here. It produces these quasi-normal modes. You can show the existence of the quasi-normal modes. But to actually get the bound, you want to look at high-frequency estimates, which requires something else. So what that requires is the following. Should probably get some space somewhere. So in terms of geometry, what the actual bounds require, for them, it's not sufficient to only look at the geodesics that are orthogonal to your favorite choice of kilometer field. You want to look at all of the geodesics then. Because in particular, you want to look at the trapping, so the trapped geodesics. So, so you preferably look at that on the frequency space or on the cotangent bundle. Just like we did for the T orthogonal ones. You see, there's nothing yet. I mean, there's no new analysis. It's just like checking geometric things. but setting up the geometry correctly in order to apply the analysis. Okay, so the second step, we want to study the trapping. So you want to show, well, what is the difference? This figure is, for one reason, very misleading. When the black hole is starting to rotate, you get all kinds of trapping. The trapping is spreading out. You get trapping of, like, I don't even know how to think about the trapping in physical space. And when A is equal to 0, it's just this one photon sphere. So you can think of it naturally in physical space, right? But as soon as you turn on A, things are going to change. And like, it depends on like the direction. Standing over here, shooting a light like geodesic in that direction might be successful in getting trapping, but you know, standing like rotating the picture, standing over here, depending on how you moved, another direction might be relevant to shoot your geodesic in order for it to be trapped. So the direction is dependent on the point where you're at if you want to have trapped geodesic. So we cannot show that the trapping is the same as in Schwarzschild because it's just not going to be the photon sphere. But what we can show is that the trapping in the phase space it's the same. So show that the trapping is normally hyperbolic. So, in other words, similar to the case in Schwarzschild, to the trapping in Schwarzschild, but in phase space. So again, we're not concerned with any microlocal analysis at this point. We're just concerned about geodesics on a fixed space-time. What you then can show is that if you think about, okay, so let's just check. I mean, to talk a bit about what I really want to say here, to connect it a little bit with, you know, as we should with microlocal analysis, we're looking at the characteristic set of the operator. Right? This is what is relevant. So this picture is going to be part of the characteristic set, like the relevant part for the trapping. Characteristic set near the trapping. So then you have the characteristic set. Well, what is that in more sort of geometric words? Well, not geometric words, but like what is it concretely in this case? Well, it's all the cotangent vectors. So either on M or M star, if you want to extend it or not, doesn't really matter for this purpose because the trapping is between RE and RC, such that the metric is light-like. It's just a set of all light-like covectors. That's what the characteristic set is. Then you can look at the Hamiltonian flow on this set, and that gives you the light-like geodesics, the dual of the dual vector corresponding to the light-like geodesic. So this is, you know, it's one condition on an 8-dimensional spacetime. So this is 7-dimensional. And how does it look? Well, here is this. The trapped set is actually 5-dimensional. So here again, like this picture is actually just, you can choose the coordinates R and the dual variable in R. That's really where everything happens. Here's a trapped set. And if you look now, so this is a 5-dimensional submanifold. You have 2 extra dimensions in this blackboard, so that gives you the 7 dimensions that we're interested in, right? So this is 5 dimensions. So it's an interesting exercise, which on good days I'm able to do it, and bad days I'm not. You can compute that the trapped set, like with thinking about it, that the photon sphere in Schwarzschild, you know, in phase space, that's naturally 5-dimensional. You know, so that's something that you might want to think about. But here it's going to be, again, it's going to be some more complicated manifold, and it's not. The point is just to understand what the light-like geodesics look very close to this trapped set. So they look like this. They have a very, very standard dynamical behavior, as is well known to people that worked with this point of view on trapping in all the other cases like Kerr and Schwarzschild and whatever. And this shows that it's indeed exactly the same also in Kerr-de Sitter. So you have an unstable manifold. The dynamics go like this. You have an unstable manifold, and you have a stable manifold here. And the trapping is the intersection of the two. That's the trapping. So yeah, with that, I conclude my talk. Thank you very much. Yes. Right. So this is obviously well, Andras is the expert of here. So this is exactly. So I mean, I would probably not go into that in detail because mostly I'm not sure I'm saying the right thing, and secondly, that's a bit. It requires some explaining. Yes, we can take it afterwards, of course. Yeah. This is my interpretation that I've heard that word before, so I think that that's exactly this. I think this is exactly this. Am I right? Oh, we haven't checked that. Okay. Yeah, I don't know the exact definition of this. Yeah. Yeah, okay. I know that you're interested in that. I have not checked anything about that. So I mean, this for example, this computation, it requires some, you know, it's basically boils down in the end to some polynomial that should be satisfying an inequality, and that there is an equality, fortunately, which turns out to be true. We found it after a long time, and I would check that equality. That would be the game. Yes. Like, my apologies, but I literally never checked the metric, so I wouldn't be able to. But you know, geometrically it seems okay. Yeah. Right. So the funny thing is that like you have some polynomial. I mean, I could even, in principle, just so that we're not talking about some abstract nonsense here. We are to some extent, but you know, concrete abstract nonsense. So the polynomial that we're interested in is this. R. So this is the mu that we're always talking about, mu prime of R mu prime minus 4 mu. And that should just be negative. That's it, between RE and RC. So now, well, how do you prove that, right? I mean, it's a strange polynomial. So you write it in 3 different ways, and all of them are necessary. And one of the ways that comes from Andras' paper, that does the job under those circumstances. And yeah, the other equalities are, especially one of them is new. Yes. That's right, exactly. Yeah. So this is it, yeah. So these are the like geodesics, or the bicharacteristics for the operator, if you will. Yeah, they go like this. So the trapping is obviously invariant under the bicharacteristic flow, but the rest of them go like this. And this comes with a statement, of course, non-degeneracy statement, that if you linearize the operator, you have sort of this in a non-degenerate way, of course. Thank you very much.